Hello, this is Math 2270 coming to you from the College of DuPage for the summer of 2020, and this lecture is entitled Green's Function. We will see in Chapter 5 that the linear second-order differential equation, here shown with variable coefficients and a non-homogeneous right-hand side, plays an important role in many applications. In the mathematical and engineering analysis of physical systems, it is often desirable to express the response or output y of x of this equation, subject to either initial conditions or boundary conditions. Today we're only talking about initial conditions, perhaps later boundary conditions. But we are expressing the response directly in terms of the forcing function or input g of x. In this manner, the response of the system can quickly be analyzed for different forcing functions. Now here's a picture that I think is worth a bunch of words. So for example, you have as input this, which is called the input or forcing function, also known as the right-hand side. Then you have a differential equation and perhaps some initial conditions that are called the system. And so taking this together with this, you get a solution, an output or response, and I again would call that a solution. Now, the approaches to date have considered this holistically together in large measure, but this time what we're going to do is we're going to split it into two approaches, and so the Green's function approach decouples the system from the input or forcing function and combines them in a way where we can derive a Green's function for the green piece. This will become clear later, but we basically set up a solution for this that will hold regardless of the input or forcing function. Now, you see the word green here and you say, I think I remember a Green's theorem, and this is the Green's theorem that you remember from at the College of DuPage. That would be Calc 3. It's the same dude, and an interesting guy, but we don't have time to talk about him right now. So here's the approach. We consider three initial value problems. So here is the full initial value problem, and notice here that I did divide all the way through by this leading coefficient, and so that means I'm assuming that it's not equal to 0, and we'll deal with that later, but that will give rise to certain kinds of singular differential equations. But we divide all the way through here blithely, and we get this. So this is a non-homogeneous differential equation with variable coefficients, and it's non-homogeneous, and it's an initial value problem. So we have y at x0 is equal to y0 and y prime at x0 equal to y1. Okay, now so that's the big problem we're trying to solve. But what we're saying is this can be expressed as the superposition of two solutions. So the solution y is going to be a y sub h plus a y sub p. The y sub h is the solution of the associated homogeneous differential equation with non-homogeneous conditions. So we're saying we're looking at y sub h being a solution to this. It is homogeneous, but we're totally including the initial conditions into this one. And y sub p is a solution of the non-homogeneous differential equation with homogeneous, that is equal to 0 initial conditions. So it's going to be this one. So you see we're packing all the initial conditions into the homogeneous solution, and we're packing all of the non-homogeneous contributions into this one, and this will be 0. So what we're doing is we're decoupling these two solutions. Okay, so we're going to focus on the solution of this equation right here at the first. Because of the 0 initial conditions, it could be described as a physical system that is initially at rest. It's 0 and 0. Position is 0 and its velocity is 0. So it is sometimes called the rest solution. Well, we know how to do that using variation of parameters. So we know that y sub p is equal to u1 of x, an unknown, y1, where y1 is a solution to the homogeneous, plus u2 of x, again another unknown, times y2 of x, where that is a solution to the homogeneous equation. And we learned in the chapter on variation of parameters that u1 prime then is equal to this one, and u2 prime is equal to this one. So we're going to solve these differential equations by integrating. So what we do is we integrate this from x0 to x, and we get this expression and this expression. But now observe that this is a constant, but I could shove it inside the integral. And this is a constant function of x, and I'm integrating with respect to t, but I can shove that inside the integral. And so I would get this. But look, I have the same denominator, the Wronskian of t. So what I can do is I can make this into one big integral where both are being integrated from x0 to x. So this is one big integral, and this is going to be, y sub p is going to be the integral from x0 to x of g of xt times f of x dt, f of t dt, excuse me. And so here is what g of xt must be. So that is how we get a Green's function for this. This is called the Green's function for the differential equation that we were trying to deal with. Now, we know, because we did variation of parameters, it's going to satisfy this equation, because that's what variation of parameters does. But we also know that if we put x to be x0, I'm integrating from x0 to x0, the integral from a to a is always going to be 0. So it gives you 0 for the initial condition at x0. It's a little bit more challenging, but if you do take the derivative, and if you take the, here's the function you have, but if you take the derivative of this, we're doing that here, y prime of x, you use a thing called Leibniz formula, and this is discussed down here. This is something you learned in your Calculus 3 at the College of DuPage, and maybe you remember it, maybe you don't. I'm not going to ask you to drive this, but that's what we're using. And so you see we plug it in, and what will happen is that I have the same, I'm going from x0 to x0, and I get 0 again after I do the calculation using Leibniz formula. So you see, this is 0 for the initial conditions, which was what I was trying to prove. Now observe that the Green's function depends only on the fundamental solutions y1 and y2 of the associated homogeneous differential equation, and not on the forcing function. You see, Green has decoupled these two things. Therefore, all linear second-order differential equations with the same left-hand side but with different forcing functions have the same Green's function. So an alternative to calling it the Green's function for the differential equation, the initial value problem, we could say that this is the Green's function for the second order differential operator that looks like this. Again, we're decoupling the problem. Okay, so let's talk about how would we do this to find a particular solution of this equation. Now look, this is y double prime minus y, that is d squared minus 1. So the solutions to the homogeneous, associated homogeneous equation are plus or minus 1, so this is y1 is e to the x, and y2 is e to the minus x, and we can compute the Wronskian of this. You should check some of these arithmetics, but that's going to be minus 2. So using our formula for the Green's function then, we end up with this. But now the minus changes the order of these, but I use properties of exponents, so what I get whenever I do the calculation is I will have e to the x minus t minus e to the minus whole of x minus t all over 2. Now maybe you remember this and maybe you don't, and it may have been in Calc 1, it may have been in Calc 2, but you talked about this function. It does come up a lot in applied math. It comes up in this course. This is the first time it does. When we do Laplace transforms, this also will come up. This is called the hyperbolic sign. So this is the hyperbolic sign of x minus t. So we know that y sub p of x is equal to the integral from x0, my initial condition, up to x, and it is the, we call that sinh also, but the hyperbolic sign of x minus t times f of t dt. Later on in this course, we're also going to talk about such a thing looking like and being called a convolution product, but not today. So that's how you would approach this in general, for a general f of t and this differential operator. But here is a problem where we're not doing this with a general f of t, we're doing it with the non-homogeneous is e to the 2x. So we're trying to find y sub p here. You know what to do, and we'll see how you do when we return in 21.1. See you.